Hello everyone, my name is Harsh and today we are going to continue with the second question of Cayley-Hamilton theorem. So if you don't know how to solve or how to prove the sums of Cayley-Hamilton theorem, then do check out my previous video as I have told how we have to solve the proof of the Cayley-Hamilton theorem. So now we are going to look at the second question of the Cayley-Hamilton theorem. So in this question they have asked us that if A is a 2 by 2 matrix, then prove Cayley-Hamilton theorem and express this equation as a linear polynomial in A. So this question can come from around 5 to 8 marks. So today we are going to look at how to solve this question. So the first part of this question is to just simply prove the Cayley-Hamilton theorem, and I have taught you in the previous video. So we are just going to prove the Cayley-Hamilton theorem. So to prove the Cayley-Hamilton theorem, first we have to consider the characteristic equation. So the characteristic equation is A minus lambda I mod is equal to 0. So this is the A matrix, and we are so for finding the characteristic equation for 2 by 2 matrix, the shortcut is lambda square minus trace of lambda plus determinant of A is equal to 0. So this is the shortcut to find the characteristic equation. So we are just going to substitute our values in this equation. So we get the characteristic equation as lambda square minus the trace would be sum of diagonal elements. So the sum of diagonal elements in this matrix are 1 plus 3. So we are just going to write this down here. 4 lambda plus, you can calculate the determinant of this matrix. So the determinant of this matrix is 1 into 3, 5. 5 is equal to 0. Now you need not to find the values of lambda, as they have not told us to find the eigenvalues or eigenvectors. So we are just going to substitute A in place of lambda to prove the characteristic equation. So we are just going to write replace lambda by A by Cayley-Hamilton theorem. So we get the characteristic equation as A square minus 4A plus 5 is equal to 0. Now we are just going to put this matrix A in this equation. So we get the matrix equation as 1, 2, minus 1, 3, 1, 2, minus 1, 3, minus 4 times of A. So that is 1, 2, minus 1, 3, plus 5. Now here you have to see that while converting a number to matrix, we have to just write down I here. So to remember this, so here it would be 1, 0, 0, 1 is equal to 0. So now you can actually put this equation in the calci, and the final answer will always come out to be 0. So if it is not coming 0, then it is your mistake. So hence we will write that Cayley-Hamilton theorem is verified. So the first part of this question is done. We have proved the Cayley-Hamilton theorem. This was a simple part. Now we are going to express this equation as a linear polynomial in A. So let's look at how to solve this. So now I have just written our question, that is this polynomial here, and our characteristic equation on the next page. So I have just written this. So now express this as a polynomial in A, we have to just do a long division method. So we have to solve this sum by using a long division method. So we are just going to divide this equation. So this divided by this. But first we have to convert this in the form of lambda, because we cannot divide a matrix by a matrix. So that is not possible. So we have to convert this equation into lambda. So you can write by Cayley-Hamilton theorem, you can write this equation as lambda raised to 6 minus 4 lambda 5 plus 8 lambda raised to 4 minus 12 lambda cube plus 14 lambda square. So now we are going to divide this equation by the log division method. So let's get started with it. So here we will write lambda square minus 4 lambda plus 5. This would be divided by, and this equation will write down here, lambda 6 minus 4 lambda 5 plus 8 lambda 4 minus 12 lambda cube plus 14 lambda square. So now we are just going to divide this by this, and you might have studied in your detail section. This is a pretty simple division. So we can just multiply lambda raised to 4 here as lambda square into lambda 4 will give us lambda raised to 6. So by multiplying this, we'll get the equation as lambda raised to 6 minus 4 lambda raised to 5 plus 5 lambda raised to 4. Now here the signs will change. So this plus will become minus, this will become plus, and this will become minus. So this and this will get cancelled out, and we'll get this as 3 lambda raised to 4 minus 12 lambda cube plus 14 lambda square. So now we are going to multiply this with 3 lambda square. So lambda square into 3 lambda square will give us 3 lambda raised to 4 minus 12 lambda cube plus 15 lambda square. And we'll change the sign here. This will become plus and this will become minus. This both will get cancelled and we will get minus lambda square and the remainder. Now you might have the question that how much times we have to divide this remainder. So the best part is that we have to divide until the power of this remainder becomes less than the divisor. So this is the divisor, and we have to divide until the power of the remainder becomes less than the divisor. So currently the power of the remainder is 2 and that of the maximum power of divisor is also 2. That means that we have to further divide this equation. So now we'll multiply with minus 1 as this is minus lambda square. So we'll get this multiplication, we'll get the answer as minus lambda square plus 4 lambda minus 5. And by changing signs, this will become plus, this will become minus, and this will again become plus. The final remainder will be 4 lambda plus 5. So now you can see that the power of the remainder is actually less than that of the divisor. So now we get to know that we have to stop here. So now we'll write the final solution as, now we know that dividend is equal to quotient into divisor plus remainder. So this is the equation, you have to learn this, that dividend is equal to quotient divisor plus remainder. So we are just going to substitute the values from this in this equation. So our dividend here is this one, our quotient is this, the divisor is this, and remainder is that. So we are just going to substitute in this equation. So we get dividend is lambda 6 minus 4 lambda raised to 5. This is 5. Plus you can simply write it dot 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 is equal to, our quotient is lambda raised to 4 plus 3 lambda square minus 1 into our divisor. Our divisor is lambda square minus 4 lambda plus 5. So just let me make a separate line here. I am writing this on the same page because you will understand that which one is the divisor and which one is the quotient in this long division method. Plus our remainder is minus 4 lambda plus 5. Now we'll replace this lambda by A by Cayley-Hamilton theorem. So we are just going to replace this lambda by A and we'll get the solution as A raised to 6 minus 4 A raised to 5 plus dot 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 is equal to A raised to 4 plus 3 A square minus I. So now here 1 will be replaced by I as we are writing in the form of a matrix. Into the divisor would be A square minus 4A plus 5I. So remember to write this I minus 4A plus 5I. So from now in previous page you can see that A square minus 4A plus 5I is equal to 0. So suppose this is equation 1. So from equation 1 you can see that the value of this equation is equal to 0. So from there we can see that the value of this part is equal to 0. So if you substitute 0 in this equation, this will also multiply with whole this part will become 0 and we will be just left with this part. So actually the polynomial form of this equation, the big one, is actually the remainder which you get from performing long division method. So now we can simply substitute from equation 1 we get that. Now we are going to write out the entire equation. Then will be equal to just minus 4A plus 5I. So now you can see this entire big matrix is only equal to this smaller matrix. So now we are just going to substitute the matrix A in this RHS. So minus 4, A is 1, 2, minus 1, 3 plus 5I means 5, 0, 0, 5. So you can just multiply 4 in this matrix and add this, we'll get the final solution as 1 minus 8, 4 minus 7. So this will be our final solution. So we have expressed this bigger polynomial as a linear polynomial in A and we have got the solution as this. So that's it guys, that was the second sum of Cayley-Hamilton theorem. And in this question, we only looked at the 2 by 2 matrix. So in exam, they can also prove CHT and express this, and they can also give a 3 by 3 matrix. So the procedure would be same, that we have to first verify the Cayley-Hamilton theorem, and by long division method, we have to bring the remainder's power less than that of divisor's power, and that's it. Then we have to just replace the lambda by A as we cannot divide a matrix in this form, and then the answer is actually only the remainder as this becomes equal to 0 by characteristic equation, and then we have to just substitute the value of matrix A and we get the answer. So that's it guys. If you have any doubt, do let me know in the comment section below. Thank you.